Today we are doing medium problem 1838, frequency of the most frequent element, and we get k at most k operations. Each operation increases a number by 1, and we want to find what is the maximum possible frequency of some element after using at most all of the operations. So I mean, the simpler approaches are that first, what are the constraints, so what is the number of numbers and how big are the numbers, because let's see, so 10 to 5 and 10 to 5 and 10 to 5 operations. Okay, because let's say we pick a value, right, and then we would just pick the closest numbers to the value. We would just pick the closest numbers to the value smaller than or equal to until we don't exceed those operations, or until we exceed, so we don't do that one. And then and I mean that would take like number of values times length, which is not great, basically n squared. Instead, what we could realize is that there is no point in trying other values than this. So we just try all values here. Now we are still at n squared, but let's say we consider values for like 4, right? Okay, 1 has to be increased to that, so we can use whatever up to k operations to increase single number up to 4, right? Then we move on, and we know how many numbers are here, right? So 2, including like the previous one, plus all of them that will be increased to this, right? And then we know how much extra operations would that cost to make it to 8. So in this case, this one takes 3, and then these two numbers to make it here takes this difference times 2, that's 8, plus 3 is 11, which is over, right? So we have to shrink our window, so we have to go away from 1. And now what do we do when we move from 1? Well, we subtract, I think, this whole difference, right? 7, so we get 4. Okay, great. And then we move here, and suddenly that's 10. That's 2 at best, right? So I guess that could work technically, so let's do it. And then we get, of course, ON solution, because we got 2 pointers. The right one just goes over all positions, and left one maybe in some iteration can go 0 position, so the window doesn't move if it would be, for example, all same elements, or the left window in one operation goes through the entire array, but once it moves to the right, it never comes back. So we just, both pointers, worst case, just go through n positions in total, not every time. So let's do like L is 0 for R in range n, and then basically what we do, so we have some sort of like current cost, right? And then what do we do? While L is less than R and current cost is over k, then current cost minus equals nums L plus equals 1. We don't want to do when L is equal to R, because it means that we have just one element, which takes 0 operations to make that. First we have to count. Do we really? Do we know? Do we have to? No, we should do R later, right? So wait, that That doesn't make sense, right? So all the previous numbers, which means that r minus l times the difference. So if r current cost plus equals r minus l times nums r minus 1, and then ans max ans r minus l, that's the number of numbers, plus 1, so that's plus 1, and then ans is 0, and then we just return answer. Don't mind the coding. Print lr, let's see. So at 0 we got 0, 0, okay. Sec 2 plus 3 is 5, so that should be enough. Like this, I think. And now this one doesn't work, that's great. Oh, they are not sorted. Oh. Okay. Now it should work. Okay. Now I'm printing, so it will. Wrong answer. What? Ah, that's bad. Because I really cannot debug this case. That sucks. Something is wrong with the logic. Shouldn't lower by this, should it? Or you know what? If I use sorting either way, I could use binary search. Or wait. Yeah, no, I cannot use binary search. Ah. Oh. I mean, so if the difference is, you think if the difference is, will be like way different. Yeah. Okay, I need a different way of calculating for each range. What is the sum needed to make the previous numbers the last number? And I mean, if we expand the pointer to left, it will just keep increasing. So my idea is to make binary search. Now we will just need to check in O1 what is the number of operations necessary, but that's easy because if we have a segment and we know the last number and we know the prefix sum of the rest of the segment, then it's basically length of segment times last number minus the first and minus 1 elements of that segment if that segment has length of n. So for that we need the prefix sums, we need to sort it, and then we need to do binary search. So let's do prefix sums for I in range 1n, pre-I minus is nums I, right? And then, I mean, we are doing n log n twice, but I mean, nobody minds, so it's okay. Now let's group the variables together, and then here we do like binary search. Good. Return answer here. Okay, and then so we have low high is 0 R, let's say, right? While low is under high, mid is low plus high divided by 2, and then we want to do if, so operations is equal to R minus mid plus 1 times nums R minus prefix of R. We start from 1 because we don't even consider the first element because nothing has to be increased to that. So prefix R minus 1 minus prefix of mid, and now if operations is over k, then we cannot increase all elements from there, so we take like the next one, otherwise we can either do mid, yeah, I'm sorry, I'm using L, so low is mid, high is mid, and then once we get that, ans max, ans R minus low plus 1. Okay, let's see, print low R 0, 1 and 2, 2. Why is that? If R is 2, print operations mid. Let's see, op mid, let's see. What? Oh, because, yeah, I'm also counting in the, okay, still wrong. How is it 4 operations? Because it's like, what the hell? R minus mid, nums R, prefix R minus 1, prefix of mid. Yeah, actually I should do plus 1 here and minus 1 here, because because I'm doing binary search also on R, so I count also like to increase to R and then I subtract it, so it's not counted. They're doing the same thing essentially. I added basically nums R to both sides, so it's still the same number, but R minus mid, nums R is 4, so there is 2 elements, right? Sum is 7, and we want to subtract mid minus 1, that's why. Yeah, and then we want to do n plus 1, and this is like 0 if I 0 else no nums I minus 1. Let's see, what the hell. So then this should be mid and this should be plus 1. Okay, finally works. Let's see, let's submit. Okay, so you for sure get the idea. No doubt in my mind, this was the cleanest explanation of all time, for sure, for sure. one test case wrong. Are you kidding? Because okay, answer is at least one. Baiting wrong answer from me. SMH. Okay, I'm absolutely behind. So there is like a linear solution or something. Let's see hints. If there is hints, I will. Okay, I can do that. I mean, I did this, but sliding window. I did this, but it was wrong for some reason. Okay, so they prove nothing, that you just try elements in there. We don't need to prove this for half of the editorial. Sorted. Okay. Okay. So basically this will cost us whatever, right? Size of windows, blah blah blah. Sort nums, left. So I did this, but it didn't work. Consider this. Add target to current, while sign multiplied by target is greater than k. I guess it works. I mean, time complexity is same, if anyone would be complaining, so whatever. Advanced sliding window. No way this is linear. This is not linear. Okay, I mean that is not advanced at all. There is some just some boring, absolutely boring trick that is ridiculous. Binary search. Okay, I did that. Nah. Okay, so that's absolutely pointless long editorial. So my 2 pointers were just garbage. I need to finish editorial before the computer dies. Oh no, it's dying. Please, please, please. Oh no. Please charge. I put it in the charger. It's not registering yet. Oh no. Let's see. Let's pray. Anyways, we can write the solution. So binary search and login. Oh, it's charging. Amazing. Okay, so intuition. Let's say we find the pick a number target to be the most frequent element. How do we verify its we can make, how do we make it as frequent as possible with k operations? We add target minus x to each x that is closest in value to target until we have operations left. Now, what can we improve in this approach. Notice that it's best to use values closest. First of all, notice that it's not optimal. Okay, that it's optimal to use just numbers from nums, since picking a larger number, since picking target +1 if target is in nums does not make sense, and picking a smaller number also does not make sense, because we should just pick the previous number in nums. Otherwise, we are just wasting operations. This is absolute dog water. Longest sentence of all time. Anyways, so we just want to use numbers from there. Okay, so since we want the closest number, let's sort them. Now, how do we find the final frequency of the of each element with k operations? Let's ask a different question first. Given a sorted subarray nums LR, what number of operations necessary to make it have the same value of nums are? Its length, or how do we write it? Its length times nums r minus prefix of r minus prefix of l minus 1. What does this mean? Where prefix r is the sum of numbers from can do this. Prefix r plus 1 is the sum of numbers from nums 0 r. Okay, and then okay, it's the length time nums blah blah blah. Okay, this is due to the fact that in the end we want nums LR to be nums R increase all length minus L plus 1 numbers to nums R, but then we subtract the actual value of the subarray, since we do not actually have to increase the values from 0, but from the real values in the subarray. Okay. Finally, we can notice that for a given R, for increasing sequence of, for given R, the number of operations needed to make nums LR equal to nums R, to make each element of nums R equal to nums R, is non-decreasing with decreasing L. In other words, as we move L, we pick more and more numbers, which will, if the numbers are same, okay, that doesn't cost us anything, or it still costs us more, I guess, only if it's equal first is equal to last, but whatever. So in other words, the number of operations is monotone, is a monotone function of a subarray of index L. So we can use binary search to find smallest L for each R. Okay. The answer is then max R minus L plus 1 over all RL, whatever, ON log N, where N nums, first sort nums in N log N, and then we do a binary search with for each of the elements which has the same as the sorting then we binary, which is the same component as the sorting, but since we do it only after the sorting, it's just n log n plus n log n, which is n log n on or o log n, which is used by the, no, it's on because we use prefix sum on, since we use prefix sums. This is long, holy, but I wanted to explain it properly so you understand. Hopefully you understand. So see you tomorrow, still in Netherlands. Bye.